Okay. So yeah, at the end of last lecture, we had started talking about ways of probing this process of information scrambling. And the general kind of idea was that what we're trying to sense is sort of the growth of an operator, the spreading of an operator over a quantum system. And that one way to do that is to take two operators that at t equals 0 commute, and then see the effect of if one of those operators spreads to sort of, if it's a local operator and it spreads to other sites, then at some later time it will fail to commute. And that failure to commute, the growth of the commutator, is equivalent to the decay of something that we call the out of time order correlation function. And we saw that kind of one way to probe that was using sort of an interferometric technique that essentially measures the overlap between the two different orders of applying the operator, so it's sensitive to that commutator. Let me just quickly ask whether there are questions from last time before I proceed into what are some other ways that this can be and has been measured, this process of scrambling. Okay, nobody's asking questions. By the way, today I'm going to try to at some point stop talking and also let you maybe calculate something. So I'm just going to give a heads up there that I would be happy if you have like something to write with in front of you, and I'm not going to just use slides the whole time today. So switch things up a bit. Okay, good. So okay, so in some sense, I also mentioned that in sort of diagnosing this process of scrambling, we're relying on some of our intuitions for sort of what we mean for when we say a system is chaotic. One of those intuitions is sensitivity to perturbations. Another one is sensitivity to initial conditions. And in quantum mechanics, that's actually a bit of a weird concept, because if I have two quantum states and I ask what their overlap is and the system evolves unitarily, then that overlap actually doesn't change with time. But nevertheless, and so you might say there is no sensitivity to initial conditions. There's not this sense of sort of initial points in phase space diverging in the way that one would have in a classical system. But nevertheless, that intuition is actually useful for thinking of another way of probing information scrambling, which has to do with basically asking about the dynamics of a system with sort of random random input states. So let me make that a little bit more explicit in a moment, but I'll just briefly say sort of one motivation for this as an alternative approach to this measurement of the commutator is the measurement of the commutator required the ability to have a system evolve under a Hamiltonian H forwards in time, but also to go back in time to attempt to undo a perturbation that required being able to switch the sign of the Hamiltonian. That is possible in some physical systems, but not always easy, as you can imagine. So kind of motivated by that, there have been recent experiments taking a different approach. And so here I'm actually going to, I was kindly given a few slides by Benoit Vermeersch, who has worked with all of the folks listed here on kind of a way of measuring information scrambling in a system that's a chain of trapped ions. And that has some tunable range of interaction. So this is something where we'll also be able to ask about kind of the spatial dynamics of the scrambling. Okay, and the basic concept is the following. The basic concept is that we had written down earlier some expression. Actually, it's unfortunate that I don't have, I actually should have kept the expression from the slide from last time. But we had written down an expression for this out of time order correlation function, which was an expectation value. Do I actually have this? I just realized I should have kept in the one slide from last time. See if I can easily do that. Okay, let's just do that to make this a little bit clearer. Great. Okay, so last time the expression we had written down. Can you see my slide?
No, not right now.
No, okay, let me, I think if I do this, do you see it or do I need to reshare?
Reshare, I think.
Reshare, okay, all right. So I just want to make sure that you remember. Now you see it, right?
Yeah, we see it now.
Okay, good. So we had written down some, again, this expression that would sort of take the overlap between applying V and then the time evolved operator W, or first applying the time evolved operator W and then going back in the time and applying V. So this kind of 4-point correlation function. Now we're going to just switch back here, be patient for a moment. Okay, so the alternative approach actually to directly measuring that 4-point correlation function with going back and forth in time actually involves some simpler measurements, but averaging over, applying those measurements to many, many different initial states. One can show in that case that this gives a way with just forward time evolution of measuring this out of time order correlator. And basically the idea is that I consider essentially a situation where I have some collection of qubits that are shown here in yellow, and I apply some random unitary operator to this set of qubits. This generically is not an easy thing to do, but it will turn out to be sufficient to apply local unitaries, so a random gate on each individual qubit, as opposed to a random entangling gate between all of them. Then we evolve the system in time, and then they perform just some local measurement, let's say. Or they do the same thing, but after preparing that same random initial state, they apply some small perturbation and then evolve the system in time, right? So again, it's a way of measuring something about the sensitivity to perturbations. But by measuring essentially correlations between the case where the system was unperturbed and the case where the system was perturbed, you can say something about how chaotic this time evolution is. In other words, if there are still some correlations, you can still sort of see something about the initial state, even after this perturbation, then that suggests that this was not very chaotic. But sort of as those correlations go away, this quantity averages out sort of towards zero, and that gives a signal that kind of decays as the system scrambles. Okay, so here's an example of an experiment that was done in a chain of, what is this? Something like 10 trapped ions. And in this case, again, just there's a random rotation performed on each site. And they evolve the system over time under a spin model that has some long range interaction. Either with or without this perturbation applied to the first qubit. So in particular, they choose this model with some long range Ising interaction and a transverse field, and they have some tunability actually of the range of interaction. Last time I told you in these trapped ion systems, the motional modes can kind of mediate interactions. So for example, the center of mass motion, if there's some amplitude to excite that can mediate an all-to-all interaction, but other motional modes can mediate shorter range interactions. And so there's actually a way of tuning how strongly one couples to different motional modes, and that allows them to tune this power law interaction. Okay, so that's kind of the setup. And here's an example of a measurement that they get in this system. So again, type 1 is the measurement where they just prepare a random state, and then they measure sigma x on a particular site after some time evolution. Type 2 is the case where they prepared a random state, instead of, but before the time evolution, they apply this perturbing operator, which is sigma z on site 1. And okay, so if the evolution time is 0, then they will see some strong correlations between the measurements of sigma x in these two cases, because there's no information about this perturbation that's kind of spread to site j, right? And again, this is kind of looking at many different initial states, and in each case, plotting like the average value of sigma x for the unperturbed versus the perturbed system. So then as a function of time, though, due to the interactions in the system, right, there's this sigma x, starts to be affected by the fact that you've flipped this spin elsewhere, and the correlation with what you would have in the absence of the perturbation goes away, right? So this is this lack of correlation is a signature of the scrambling in the system. And again, this relies on taking these many different data points for different initial states. And then one can even start to ask questions again about kind of how the information is spreading under the influence of these interactions. So here, the perturbation is always applied on site 1, but they measure the spin on some other site j. So the different colors here are which site did we measure on. And so if you measure in the nearest neighbor site, then that has an effect quite quickly on this, out of time order correlator decaying. If you measure on some site further away, then there's kind of some delay before you start to see the decay. So left is experiment, right is theory, which they can do because it's a chain of 10 spins. So this nicely shows in kind of a protocol that just requires good control over the initial state and just a projective measurement that you can directly see this effect of the operator spread. Okay, one other thing they can do with this is actually ask the question, is there some sort of like characteristic velocity that there's like a front that's spreading at some velocity that describes sort of how long does it take for the perturbation to get from site 1 to site j. If they sort of plot this decay in a way where they're plotting as a function of time minus distance over velocity, these curves sort of collapse onto each other. In the case where this exponent is larger than 1. If the power law starts to become very weak, so the interactions are very long range, then it's kind of less clear whether this is the right way to think about it, whether there's this characteristic velocity in the system. And so those are the types of things they can start to probe in this system by having the tunability of the interactions and the ability to measure the commutator. The ability to measure this out of time order correlator, even without directly doing any sort of time reversal. So this is nice, and this is actually sort of applicable to a much wider range of experimental platforms than things where you need to be able to switch the sign of the Hamiltonian. Questions about that scheme?
So I might have just missed this, but I guess when you mentioned starting with this random initial state, were the random unitaries localized to each site, or do you like generate entanglement between sites in the random unitary?
So ideally, one would have like really a completely random unitary that could include generating entanglement between the sites. But it turns out that it is actually good enough to do local unitaries on the individual sites. I think the fact that you've done these local unitaries and not a completely random unitary is something that needs to be accounted for in some way in the analysis. And I don't remember the details of that, but that's in the paper. So I would, if you're interested in kind of, getting deeper into this, I would definitely refer you to, this is the experiment, but there's also a theory paper from a year before with Ramesh as the first author. And that really gets into sort of why exactly does this work and proving that it works, and to what extent does it matter whether you have a completely random unitary or just local ones. But the bottom line is thankfully for experimentalists, local random unitaries are sufficient.
Thank you.
Okay. Other questions? So one other kind of neat result that I'll just mention, just as a theoretical result, this is from my colleague Xiaoyan Qi. He has pointed out that if you do this type of experiment where you kind of prepare random initial states and then just measure some simple local observable after time evolution, there's actually a direct way to get out something about the size of the operator representing that local observable from the statistics of the measurement outcomes. And in particular, kind of the picture that one can have is if let's say, so here I have some spin model, it's an Ising model in a transverse and longitudinal field that should be chaotic. The basic idea is that as one can, if you consider sort of a single initial state, and I have a system that is not chaotic, then kind of as a function of time, if I measure some observable like sigma x on a particular site, and I measure the expectation value of that observable, that expectation value will tend to kind of it'll have large, the fluctuations from one initial state to another will be large. But if the system is chaotic, then the expectation value itself tends to decay over time for a given initial state. And then as I sort of look at many different initial states and ask what are the fluctuations over those different initial states, then those fluctuations are actually small because the chaos itself gives you kind of an averaging in the expectation value for any given initial state. And so like if the operator has size n, one can, Schleier was able to actually prove that the size, the fluctuations basically go as 1 over the Hilbert space dimension to the power of the operator size, right? So the bigger the operator, the smaller these fluctuations. And so that's kind of a neat kind of quantitative relationship between fluctuations that you can measure by preparing many different initial states and the size of the operator. So that starts to get kind of quantitative. Okay, great. So there are kind of these, you know, 2 different examples I gave you of how you might probe scrambling, and I'm going to get into a third. Before I get into a third, I wanted to just say a little bit more about, you know, the question that came up. What are some systems you might use if you want to see, or what that have been proposed if you would like to see fast scrambling? And so actually, just to, as a sort of quick check to see whether people are following, I showed a few different experiments quantifying scrambling. In anything I've showed so far, was there a fast, were any of the things I showed you so far fast scramblers? Meaning that the characteristic time scale for this out of time order correlation function to the k is only logarithmic in the number of qubits. In this case, they were all kind of systems of qubits, for the number of sites. Was anything a fast scrambler? Is anyone willing to answer that question? Yeah, Casey, I saw you unmute yourself.
I don't think there was any once. I can't remember all of them.
Yeah, I showed a few different physical systems. Yeah, so last time I showed something that had like global interactions that wasn't even chaotic, or anything with global interactions. You sort of don't have that exponentially large Hilbert space in which to even talk about fast scrambling. And then we showed something with local interactions where there was this typically sort of some velocity, right, at which correlations spread. And that means that sort of the time to spread over the full system is going to be kind of linear in the system size. Marcus?
That's it. I just want to make sure I get this straight. So if we want fast scramblers, that means there's a log relationship between the time and space quantities. Is that correct? Between the time and basically one way to think of it is it's really sort of the log of actually the entropy is one way to think about it. But if I have sort of I start with some infinite temperature state of n qubits, that would just be the number of qubits. Make sense? Yeah. And in fact, so let's actually just make that a bit more precise. So the basic, right, the conjecture would be that if I have something that is scrambling information like a black hole, there's some characteristic time scale for sort of local quantities, local perturbations, local observables to equilibrate, perturb the system. And that, if it's a thermal state, would be something like 1 over the temperature. And then the idea is that in terms of that characteristic time scale, and this is something actually Tom asked the question last time about sort of what is the Lyapunov exponent? Is that something you can probe? Another way to think about it is the temperature sets kind of a Lyapunov exponent, which is a characteristic time scale for the chaotic behavior of the system. But for a perturbation to spread over the entire Hilbert space, right, that's longer than just local observables equilibrating. And that could be longer by, well, the fastest that this could go is that it's this characteristic timescale times the log of the entropy of the system, where again, if I have n qubits, that entropy kind of just scales as n. Now, the sort of intuition for this, one nice intuition for this comes from thinking about a random circuit model, where you say, imagine that I have, instead of the temperature setting, sort of 1 over the temperature being my characteristic timescale, if I have qubits, then it would be the gate time, if I'm like doing discrete gates. And you could imagine if I want to sort of quickly have information spread from one to many, what I could do is sort of in a given time step, connect each qubit with some random partner, and then reconnect again. And if I kind of randomly reconnect, then sort of information will spread from 1 to 2 to 4 to 8, and kind of in a logarithmic number of time steps, it will spread over the entire system. So that's kind of the intuition for how fast scrambling can happen, how you can get this logarithmic time scale. And that's why kind of the local interactions tend to not do that. You need something that is more non-local. So I saw someone maybe show their face or unmute themselves. Was there a question? No, maybe not. Okay. Yeah, Vincent. I can't actually hear you, Vincent. I can see you, but I can't hear you.
Oh, sorry. Can you hear me?
Yeah.
Okay. Yeah. So I guess in these models of fast scrambler, you kind of need all-to-all connections, which effectively, like, does that effectively always make the dimension 0 for the types of spin models that can actually be engineered?
What do you mean by making the dimension 0? You're just saying it's because it's all to all, it's 0 dimensional. I mean, I think there's a question about, does it mean that like physically your system needs to be 0 dimensional, whatever that even means. I mean, physically, I guess your system is always going to have some non-zero dimensionality, but sort of effectively, yeah, in some sense, I'm actually not quite sure whether it's better to think of it as 0 or infinite. Or actually, one way that I like to think about it is if you have kind of a hypercube in log n dimensions, then the radius, and then you can sort of get everything within a radius that's log n. And it's probably true that if you have a random graph, it actually approximately ends up being something like that. But that's a little bit hand wavy. But I don't know, does that answer your question?
In a way, I guess I'm just trying to confirm that, like, you know, there's no, maybe another way to pose it is that to ask whether there are models that have like nearest neighbors in 1 or 2D that.
Yeah, so if it's a low dimensional system and you just have nearest neighbor interactions, that will not give you fast scrambling.
Right.
Yeah. Tom, do you want to add to that? Yeah.
So could you have like puddles, like a bunch of these, you know, and then connect them by
this is a really good question.
Nearest neighbor.
So I think there's also a question about sort of there's a question about what do we mean by fast scrambling? And there are sort of two senses in which this is used. One of which has to do with this characteristic time scale that's 1 over 2 pi times the temperature. And in general, like things can go slower than that, but nothing can go faster than that. And then the second one has to do with how long does it take for operators to kind of spread over the entire system. And so in terms of this sort of having information spread over the entire system, if there's a sense of locality, even if it's like individual puddles, right, you're still going to have some velocity, right, some characteristic velocity. But you can make it as fast as possible. You can engineer the individual puddles to saturate this bound that's this 1 over 2 pi times the temperature. And that's something that people think about. So they think, we mentioned the SYK model. People think about sort of puddles of SYK-like models so that you can saturate this 1 over 2 pi temperature scaling of the Lyapunov exponent. Does that kind of answer? Does that address your comment, Tom?
Yeah. Because I mean, those are also interesting from a holographic point of view, I would say.
Yeah. Okay. Great. Yeah. Mm-hmm. Good. Yeah. Okay. So various people have thought about, how might you actually engineer things that behave in this way. And there's a set of proposals in solid state systems. So just to give an example of this, there's a proposal from the group of Marcel Franz, which is basically thinking about a system where there's essentially a graphene flake with some irregular boundary. So it's kind of this disordered 2-dimensional system, and it's in a magnetic field. And essentially, in this case, one has basically in the lowest Landau level, the wave functions have some kind of non-local, almost sort of random looking structure. Some of them are shown here. And so it turns out that in this case, if you sort of look at the scattering between these delocalized wave functions, because of the delocalization, they're kind of all coupled to each other. In the precise coupling depends now on the structure of these wave functions, which is set by this irregular boundary. But the nature of the scattering actually does look like something where if like the C dagger and C represent like hopping between these different orbitals. And so they've proposed that you can actually get an SYK-like model where you have this sort of non-local hopping. It's non-local in the sense of, if I think of each of these orbitals as a site, because the orbitals themselves are spatially delocalized, this can give rise to this kind of this random structure of couplings between them. So that's kind of intuitively one way that one can hope to build these systems. This is something that maybe is not so amenable to kind of the toolbox I was describing. That's more that if you have atoms or qubits that that you have a high degree of control over, how do you measure scrambling? Here you would need different types of observable spectroscopic observables, for example. And then, I guess, I talked about atoms in cavities, which is yeah, sorry, go ahead. Yeah.
Sorry, I had a question. So can in this design, is the hexene shape, or sorry, the six-sided shape have to do with the geometry? Is that a geometry factor? That it's like a maximal tiling shape? Like, is there a
does it have to be six-sided?
On a two-dimensional setup? Or is there a more maximal shape? It just seemed like there's a tiling reason that you'd maximize volume to area here, but
I'm not aware. So my assumption was that this shape is just because graphene is a system that lots of people are working with in the lab, which for various reasons why it's interesting, right? But so this was just thinking about what is a system that people have access to in these solid condensed matter experiments that would allow you to realize a model like this. And I don't think the six-sided shape is particularly important, but it's more about the disorder and the way that these eigenstates are kind of spatially delocalized and disordered in such a way that gives you a random coupling between them. Yeah, okay. So then, I mentioned situations where we have spin excitations whose hopping is mediated by photons, and that can certainly give you something non-local. Just to be like, so what are kind of the biggest challenges and why haven't we looked at fast scrambling in this system yet? The challenge is really having highly coherent interactions between, let's say, individual spin half degrees of freedom. So one of the challenges is just the photons can leave. And so we work really hard to make that probability as small as possible. That's sort of the experimental side and the engineering challenge. And there are ways of getting that better and better. But anyway, if you have any dissipation, that's going to limit your ability to sort of probe this phenomenon of chaos. And so, on the technical side, I'm always interested in how can we make these systems more and more coherent. The other thing one can do is ask, can you extend some of these ideas to other physical platforms? And in fact, for example, the trapped ion platforms are somewhat analogous. Phonons mediate the interactions, and the ability to have sort of coherent interactions between individual qubits is that's so far better in the trapped ion platforms. So some of these ideas can be extended to the trapped ion platforms. But another proposal that was recently put out has to do with systems of atoms interacting by coupling them to Rydberg states. This is also something where very coherent gates have been realized just in the past few years. And I think I showed some pictures the other day of these systems being very scalable. You can have an array of hundreds of them that you look at individually. A point that has been recently made is actually, if you can take the atoms and you can move them around, and that's actually possible. So each one is trapped at the focus of a laser beam, and there are ways of sort of moving them around. Then you can start to basically, in some effective, but by the time dependence, I have, let's say, nearest neighbor interactions at some time, but at some later time, I have second neighbors or fourth neighbor, what were the second neighbors now start to talk to each other, you can kind of engineer more complex structures of interactions in principle. And so that's been proposed as another way of realizing this kind of fast scrambling in a system that also has sort of been demonstrated for having very coherent interactions and high entanglement fidelity for gates between pairs of atoms. So these are kind of some directions that I think this is one that's likely to be explored soon in experiments. And so there are directions for even seeing the kind of fast scrambling behavior. And then this would also be, actually coming back to Tom's question, a natural platform for also asking though about the interplay between, like, if you had puddles with some non-local interactions, but also a spatial dimension, asking about transport in that type of system. So those are just a few examples. There are lots more papers. I didn't want to go into too many of them, but just to give a flavor that actually I would say that the field is rapidly progressing. All of these capabilities are sort of being developed at the same time that the ideas are coming out about what you might want to do with them. Okay. Questions on that? Otherwise, yeah, let me pause and ask whether there are questions. Okay, so if not, I thought I would move towards one other class of experiment that's recently been done in this idea of probing scrambling, which is inspired by ideas for how would one, if you have a qubit that falls into a black hole, how would you decode the Hawking radiation to find out what that information was? And so this is basically a set of protocols that have to do with quantum teleportation. And just to kind of illustrate, I want to start by kind of illustrating the connection to the idea I showed before of sort of interferometrically measuring scrambling by a measurement of the commutator. So in order to do that, I'm going to switch in a moment to something I can write on, but maybe I'll just briefly flash up some references and say that most of what I'll say is based on this nice theoretical paper called Disentangling Scrambling and Decoherence via Quantum Teleportation by Yoshida and Yao, which inspired a couple of experiments in trapped ions and in superconducting qubits over the past couple of years. So good. So let me just reconnect for a moment. With an iPad. The iPad, for some reason today, some days it just does AirPlay, some days it wants a cable. Today it wants a cable. Good thing I have a cable. Sorry for the delay. Go. Excellent. Okay, you see this, right?
Yes.
Okay, maybe we should let it rotate so I think it'll be bigger. Okay, so let me actually just copy, copy quickly a picture that we had last time. Okay, so last time we had kind of talked about an interferometer that you could build in order, and that actually has been built, for example, in the Google processor for probing this commutator between some local operator V and some other time-evolved local operator W. right? And we gave an example where you have a control qubit that dictates, do you apply V and then the time evolved W, or do I first evolve in time, apply W, and then go back and try to apply V? So one way of doing this is if you have some qubit controlled operation. But another way of doing this in principle is actually if rather than just having a single copy of this quantum state psi, you have two copies of the quantum state. So this actually gives another way of doing this type of an interferometric measurement. And this idea, this general idea I'll just briefly mention of having sort of two entangled copies of a quantum state is quite powerful. I'll say now sort of how it relates to measuring scrambling, but it also, for example, is a tool for measuring entanglement entropy. This is a very powerful tool if you can do it. And so the basic idea, so let's just be explicit when I say we have two copies. What I mean is that rather than just having this state psi, we have, let's just call it psi twiddle. We have some kind of a sum over basis states and I'm actually going to use colors carefully. So, okay, so we have some sum over basis states of kind of, one system being in state J, product with the other copy being in state J. I guess we can divide this by the dimension of the Hilbert space for each system. So if it's a qubit, the D is just 2. If I just have one qubit. Okay. And so the idea is that this is a state that for, if I look at either system alone, either copy alone, and trace over the other one, the state looks kind of flat random, but in its entirety, the system is in a pure state. I guess some of you have heard the term thermofield double state. This would be the infinite temperature version of a thermofield double state, where generically that would be something that looks thermal for either system by itself, but is pure for the combined composite system, infinite temperature thermofield double state. Okay. So if I can make that state, then what can I do with it? So it helps, let me first sort of develop some notation that's going to be useful for us. So we'll define, so if simple example that we'll actually end up working with is the case where this is a single qubit, let's say, and in the single qubit, this type of a state is well known as an EPR state, right? Like 0, 0 plus 1, 1 over √2. Let's just call it that. And just to sort of develop some nice graphical notation, we can kind of represent this. If I have a pair, two copies of the system entangled, I'll represent that by, I won't use color forever, but for the moment, I'll use it just as sort of a guide. So the blue and the red are representing sort of my two copies of the system, right? So this is going to represent, like if it's just a single qubit, this would be representing 0 cross 0 plus 1 plus 1 over root. Okay, so that's just notation. And if I wanted to take like the permission conjugate of that, I would represent that like this. And now, suppose that instead of kind of what I drew, I'm going to just draw a slightly modified version now of my interferometer. Which is that I'm going to start with this EPR state. And I'm going to apply one set of operators on one copy of my system, and the other set of operators on the entangled copy of the system. And at the end, I'm going to actually project onto the EPR state again. Questions about what the notation means? Let me first make a slight modification. This is actually going to be important so that we get the right result. What we'll do, so actually just to be clear, so this was V, this was the time evolved operator W. And it turns out that what we're going to want to do, so this was, I just copied this from the previous page, but I'm actually going to want to apply the complex conjugate of everything on the other side. So let's slightly modify this. Star, this is going to be, and I'm going to try to convince you that this does the same thing. Okay. Transpose, this is going to be.
Can you write this out in terms of bras and kets?
Yes, I'm about to do that. Thank you. Good. So yeah, okay, so what is this? So this is basically saying, and you have to kind of read this, yeah. So the initial state that I start with over here is just, I'll write it as EPR. Is everyone okay with that? We defined that just a moment ago as this state if it's a single qubit, and generically this kind of a state. That's two entangled copies. And this is basically saying that what I'm going to do is I'm going to act on, let's actually also explicitly maybe label these two copies 1 and 2. Right, these are my two entangled copies of the system. And this is basically saying I'm going to act on subsystem 1 with, let me, so that I don't have to write out too many symbols. I'm going to define the time evolved operator, again, as just WT. Okay, so this is basically saying I'm going to act on subsystem 1 with V followed by WT. Okay, so that means I'm going to apply WT to subsystem 1, to be very explicit here, followed by applying, sorry, this is V followed by W. I have to flip the order when I write it in this notation. So I apply, right, V and then W on subsystem 1, tensored with applying applying on subsystem 2. On subsystem 2, I'm first going to apply W star, and then I'm going to apply V star. So V star and WT star. This is all on subsystem 2. I'm just going to write that below. Is that okay? So this is saying I'm going to, right, I'm going to apply, yeah, V followed by W to one copy of my system, and V star, WT star to the other copy of the system. So, right, so here, just by acting on sort of the two different halves of this entangled system, I'm essentially building up something that is going to be equivalent to the interferometer from before. Does the sort of the diagram and the notation, do those make some sense?
Good.
Okay. And then, so one other thing that's really sort of useful to know about this, these EPR states is that they have the nice feature that if I apply some operator, let's just call it O, to one copy of my system, that's actually the same as applying the transpose of that operator to the other copy. Simple examples that you can, if you want, sort of, you can go through this on your own time. If I take literally just the state for a single qubit, you can pretty easily convince yourself that if I apply the Pauli Z operator, it doesn't matter whether I apply it to one qubit or to the other one. Same thing if I apply the Pauli X operator. If I apply the Pauli Y operator to one side, that one isn't the same as its transpose. And so I need to transpose it and apply it to the other side in order to have the same operation. But essentially, by kind of the symmetry of the state, the entanglement between the qubits, more or less applying a given operator to one side has an equivalence to applying it to the other side up to this transposing. Questions about that? Does that seem believable? Questions about that so far?
And then are you completing the formula that you wrote with Bras and Ketz by taking the overlap onto the EPR state at the end?
Good. So in this formula for the full diagram, this last part means we're at the end exactly taking the overlap onto the EPR state. Great, thank you. Okay. This equivalence that I just drew actually means that, for example, having this V star down here, I could equivalently write this as having the dagger applied up here. So this would be equivalent to putting the transpose on the other side and not doing this. Let's just simplify that. So this would be another way of measure. So this is basically saying this is a way of measuring, right? This, if we wrote it down before, we call this function f. Equivalent with the transpose up here. Transpose, sorry, the Hermitian conjugate up here. Okay, and so this actually tells us that if I can prepare, for example, let's draw a little box around this. If I could prepare this state, which means if I can prepare a state, I don't know, let's call it psi prime, that involves applying V and U to one half of my system, one copy of my system, and applying U star to the other copy of my system. State. Then actually this out of time order correlator would just be given by projecting, or sorry, taking the expectation value of W acting, let's say W on one, and W star on the other, in, sorry, not in the EPR state, but in the state psi prime. Okay, so this starts to give some idea that if you can prepare sort of two entangled copies of your system, then that gives sort of an alternative way of sort of, you're almost using, interfering the two copies with each other in order to measure this, as opposed to, let's say, using a control qubit to build your interferometer. So that is, you know, that's sort of another approach to measuring this out of time order correlation function. But actually the thing that kind of inspired this approach, so this gives sort of a recipe for preparing for, you know, in principle, measuring one particular out of time order correlation function involving these operators V and W. But it turns out there's also, if what you care about is sort of just overall, not specific how much information has spread between 2 points, but just some kind of averaged out of time order correlation. So average that correlation function over all possible operators, which gives you a generic measure of scrambling. It turns out that there's a protocol that's essentially based on quantum teleportation, taking advantage of having kind of this entangled state that gives you a measure of this average out of time order correlation function that quantifies scrambling in the system. And this is actually inspired by, let me just maybe copy a picture. Let me just look up here for a second. So I've copied this nice picture. This is inspired by a thought experiment due to Hayden and Freskel about sort of the question of if Alice, I guess in the original paper, Alice throws her diary into a black hole because she's trying to hide her private thoughts. But actually, from the Hawking radiation that leaves the black hole, Bob has a way of actually sort of deciphering Alice's diary. And the general kind of concept, and there's actually sort of a specific protocol for doing this, which involves if Bob sort of understands the black hole well, and in fact, even makes his own copy. So sorry, what's what here? So U represents the black hole, right? So Alice has some state that she throws into the black hole. U is some operation that is scrambling, right? This is kind of the chaotic scrambling of the black hole. And D represents some Hawking radiation that Bob can collect. But the other thing we're going to assume is that Bob actually makes himself kind of a copy of the black hole that's entangled with Alice's black hole. So he understands these dynamics well. He knows how to implement U star, okay? And here, this is showing that there's some EPR pair that is shared, so there's entanglement between Alice's black hole and Bob's. And the idea is that actually by doing a suitable measurement on the Hawking radiation from the two black holes, Bob actually can teleport the information that Alice threw into her black hole onto sort of a reference qubit that is in Bob's possession, and that's entangled with his black hole. So that's the idea. And so I want to kind of give a bit of a flavor of how that works, because the neat thing is actually by asking things about what is the probability that Bob gets a certain measurement outcome when he measures the Hawking radiation, and also what is the fidelity of successfully teleporting Alice's qubit. These actually give information about the scrambling of this system. And that's been demonstrated now in a couple of experiments with ions and superconducting qubits. Okay, so let me kind of scroll to a blank page, and let's just sketch that circuit for ourselves one more time. So the idea is that we have Alice's state A, and this is Alice's black hole. That is entangled with Bob's black hole, U star, and that is also entangled with Bob's reference qubit. And let's just give these names because it might be useful. Let's call this Q0. This one is qubit 1, qubit 2, qubit 3, and qubit 4. Okay. And okay, so this is just Alice's black hole and Bob's black hole. And then in order to actually try to decode the Hawking radiation, it's coming out here, what Bob is actually going to do is to perform a measurement that projects, draw that the right way, 2 qubits, one coming out of his black hole, one coming out of Alice's, onto the EPR state. So generically, the probability that he measures this pair of qubits to be in an EPR state is, it's not certain that that's the measurement outcome he will get. But actually, if this is a scrambling unitary, then with high probability, he is going to have actually Alice's qubit is going to end up being teleported to here. So I want to go through just a couple of examples to kind of give a flavor for this. And so the idea is this is a sort of a probabilistic decoding protocol conditioned on a certain measurement outcome, which is that this pair of qubits is projected into the Bell state. We would like to get Alice's state out at this point. There are actually ways of making this deterministic. we'll focus on the probabilistic case. So just as kind of, let's do two simple examples. So simple examples. So first of all, let's consider the case where this is not something that scrambles, but where U is actually just the identity operator acting on 2 qubits, okay? So actually, maybe we can just sketch that here. So simple case where U is the identity operator, that basically means I'm going to take my qubit A and nothing will happen to it. I'm going to do this projection of the Bell pair onto itself, right? Because each of these U's does nothing. And I end up also doing nothing to the reference qubit that's entangled with Q3. So, so two things you can ask. This is kind of a trivial example, but one is what is the probability that we actually project, that Bob sort of successfully projects qubits 2 and 3 onto this same EPR state that we started with. That probability is, does anyone want to shout out what it is? Very easy question. Meant to be easy. You're listening. What is the probability that the projection?
Probability 1.
What's that?
Probability 1.
Probability 1. Good. Yeah. Sometimes people are afraid to answer easy questions or embarrassed. Okay. Good. Thank you. Okay. So good. Yeah. This succeeds with perfect probability, and the fidelity. So if we, let's say that let me actually write some notation. So let's say the input state that we had here, let's say psi in, and just that's going to be A cross, I'm actually going to call this EPR state phi. There's also another common name for this EPR state. I'm just dealing with qubits. So 0, 0 plus 1, 1 over root 2. Okay, so that was our input state. And then we can ask what is the fidelity of teleporting Alice's qubit, which would be if I say that sort of at the end, the system is in some output state. I guess we can just call it like if I just call this thing, this is psi out. So let's say psi out is a normalized state, so conditioned on doing this projection, the state at the end of all of this. So then we can ask what is the fidelity, which is basically the overlap of Q4 being in Alice's state. So let me write that with A4. Psi out, that thing squared, right? So what's the probability that Q4 is measured to be in Alice's state? That would mean we successfully teleported the qubit. What is it in this case? Any thoughts on that? What is the probability? What is the fidelity of teleporting the qubit in this kind of trivial example?
Okay, I probably will get this wrong, but I will try. Is it 0? It doesn't look like it went to Q4. It looks like it's just traveled along Q0. Is that right?
You were a little bit quiet. So can you say that? It doesn't look like it's at Q. It looks like it sort of stayed at Q0. Is that what you said?
Yeah. I said it kind of looks like it's at Q0 still.
Yeah. So it looks like we haven't really affected Q4. Q4 is still entangled with Q3 in this EPR state. Given that that's the case, so basically Q4 is just part of an EPR pair. If I project it onto some particular qubit state, what's the probability that I'll just by chance get the right result? The half. Right. So simple example, if Alice's state were 0, right? Q4 is part of an EPR state that looks like this with 50% probability, I'll just get the right answer by chance because it's just one qubit. That will go down if this were a higher dimensional Hilbert space.
I see. Okay, thank you.
Right, the probability of just getting it by chance. But in this case of a single qubit, it's a half. Okay, so good. So this is not, okay, so this is a case where the thing doesn't scramble, right? In the case where we don't have scrambling, then with, in this example, actually with perfect probability, we project onto an EPR state because that's what we started with. And there's is some possibility that you'll happen to get Alice's state out here if you measure on the right basis, but that's just the trivial sort of, that's what you get by random chance. If you just prepared a random state of Q4 with 50% chance it would be the right state if you measured it in Alice's basis. Okay, that's what that means, that this fidelity is a half. That means you haven't won anything. Okay, so that's just the trivial example. Now let me try to walk through one more example. I was hoping to let you do this, but I'm not quite sure at the time. Okay, so the second example we can do, and actually I'll switch to a place where I have the circuit sketched out. The second example we'll do is consider the case where this operation is a C0 gate. So just to give an example of what might happen if we have a simple gate that entangles these two. I don't really want to use a random unitary, so it's annoying to calculate. I want to give some intuition from a simple case. Okay, so if I had, for example, a C0 gate here, then so so U here is my C0 gate. It means if qubit 0 is in the 1 state, we'll flip qubit 1. If it's in the 0 state, we'll do nothing. And then the correct way that I have to draw this upside down now for the other for Bob's system. So Bob's Q3 is going to act as the control for possibly flipping Q2. Okay, so that's what that would look like. And now we can ask the question in this case, what's the probability that we project qubits 1 and 2 onto this EPR state, and what is the fidelity with which we teleport Q0 to this output port if we measure the EPR state here. Okay. I guess I'll keep my screen share, but if you have something to write with, maybe you can try to work through this and not just watch me write. Okay. So what am I going to do? Let me just copy the picture. So I'm going to define some notation. Because we start with, let's say, Q1 and Q2 in this EPR state 0, 0 plus 1, 1 over root 2. If we were to, let's say, flip one of the qubits, then you would end up with a different EPR state, which is 0, 1 plus 1, 0. This is one of the Bell states. This is another one that is equally entangled, but has a slightly different form, right? So this is orthogonal to the previous one. If we flipped one of the bits, just one of the qubits, we would transform 0, 0 plus 1, 1 to 0, 1 plus 1, 0. So it's going to be useful actually to kind of have these two states in mind. I'll call one of them phi plus and the other one psi plus, which is standard notation. Okay, so in this example, if we were to kind of work our way through this, let me just copy this picture onto a page that has some space to write. Okay, so the first thing we would do, let's define Alice's state as A0 plus B1 over root 2. And no root 2, sorry, A and B will already be properly normalized, A0 plus B1. And now what this is going to do is it's basically going to say the input state is going to be converted into, let's define psi1 as this first unitary operator that acts on qubits 0 and 1, acting on my input state. And what this is going to do, let's just actually remind ourselves. So our input state is A0 plus B1 over root 2 cross 0, 0 plus 1, 1. I keep putting a root 2 that I don't want. Way. Cross 0, 0 plus 1, 1 over root 2. Okay. And so, for example, when I act with this first unitary, this top unitary operator that is a C0, it's basically going to say nothing is going to change if Alice's qubit is in the 0 state. So we have a component of this that's A 0 cross, this is 5 plus, 5 plus, cross 5 plus. But if Alice's qubit is in the 1 state, then we're going to essentially flip one of the qubits in this EPR pair. And so Q1 and Q2 are now going to be in the state psi plus, that's the one where one of the qubits is flipped, which is orthogonal to the one we started in. And so far, I'm only applying that first unitary. So the next qubit is still going to, the next pair of qubits is still going to be in the Bell state it started in. Do you agree with that? Yeah, okay, cool. So now we can take this a step further and apply this second unitary to the system. And the basic idea is going to be the same, right? So but now we kind of need to, okay, so you can write out some algebra. I think because we don't have that much time, I won't go through all the steps. If you want, you can kind of go through this for yourself later. So let me take just sort of one step ahead and write out what we get and then see whether it makes sense. See if I have this here. Copy this for a second. If you want, you can go through this carefully on your own time. But in this example, if I define, let's say, psi 2 as U star is actually the same as U acting on qubits 2 and 3, applied to psi 1, right? So now I'm just applying this second gate here, acting on psi 1. What I'm going to get out is something that I've written out here, but let's try to parse this. So essentially what we're going to have is two possibilities. A is in the 0 state, and then we're either going to have these last two qubits being in 0, 0, and the middle ones being in the state they started in, which is 5 plus, or the last two qubits are in 1, 1, and the middle ones are in an orthogonal state. In the case of if B is in the 1, if Alice's qubit is in the 1 state, the middle qubits are only going to be in that same EPR state they started with if the last two qubits are also in the 1 state. One way to think about this is kind of basically in this example, the only way that the middle two qubits will end up in the original EPR state is if either no qubits got flipped or both qubits got flipped, right? And one of those flips is controlled by Alice's qubit. One of those flips is controlled by sort of part of this EPR pair at the bottom. And so this ends up giving us a state where if we project onto the middle, this sort of middle pair of qubits still being in the EPR state it started with, the relevant parts always have actually Q3 and Q4 in the standard basis of sort of the 0 and 1 states, Q3 and Q4 have the same value as Alice's qubit. So this ends up giving me something where sort of my output state after projecting onto the EPR pair in the middle in this example would be A000 plus B111. Okay. Right, so basically these are the only two ways that, so either this was in the 0, 0 state and Alice's qubit was in the 0 state, and then nothing happened to the middle, or Alice's qubit was in the 1 state, this was in the 1, 1 state, and then we did two flips that left that sort of brought us back into this 0, 0 plus 1, 1 state in the middle. Okay, so
Monica, you
yeah.
have 5 minutes.
Oh, okay. Thanks for telling me. There's this weird thing where my iPad clock doesn't evolve.
Yeah.
So I knew I was
Yeah.
getting close, but I didn't realize just how close. Okay.
I'm familiar with that. Yeah. Okay.
So I'm glad you told me. Okay. So now there are just a couple of things to sort of that we can think about. One is what is the probability in this case that we actually project onto this state and not an orthogonal state. So actually, can anybody tell me what is the probability that I project onto that original EPR state that I started with based on what I've written down here? So if I kind of look at, this is a kind of a messy thing, but if I look at sort of each half of it, here I'm in an equal if Alice's qubit is in state 0, I'm in equal superposition of the 0, 0. Sorry, let's be careful here. So the thing that we're projecting, let's actually just red line a little bit shorter. So the part that we're projecting is this one. And so with 50% probability, we get phi plus. The other half of the time, we're going to get psi plus, which is an orthogonal state. And the same thing if Alice's qubit is in the 1 state. So you can kind of see from the structure, from the symmetry, that the probability that we will project onto the EPR state is a half. Okay, so that actually went down now that we did some kind of entangling, not too surprising, right? Like earlier when we had the identity with perfect probability, we ended up in the state we started with. But if we entangle Alice's qubit with Q1 with the C0 gate, then this probability goes down. The fidelity of getting Alice's qubit out. Let me just, well, actually, you can kind of see it from this structure here. That if I ask sort of what is the overlap of psi out with Alice's state on qubit 4, it actually doesn't matter which qubit it is because these are all the same. These all have the same value in the standard basis. If I ask what the overlap is, and I square this, I'm going to end up getting actually a to the 4th plus b to the 4th. So I'm going to basically get projecting onto the state A is going to give me an a squared and a b squared, but then I'm going to take the norm squared. Okay, so a couple of things we can actually see from this. So this isn't unity fidelity. It could be unity if, for example, A is 1 or B is 1, then the fidelity, so this is the fidelity of teleporting the qubit would be 1. So if I happen to choose the 0 or the 1 state for Alice's qubit, it would actually successfully end up here. This doesn't perfectly teleport though in any basis yet. So this isn't perfect teleportation. One thing we can say about this is that the lowest that this could be is if A and B are both 1 over root 2. Then this would end up being a 4th plus a 4th is a half. So we're going to end up with this fidelity being between 0 and 1. So sort of an average case scenario, remember if we did the identity, then, or if we just randomly guessed some state for this qubit, the fidelity would be a half, but in sort of an average scenario, it will be higher. But U is not yet an operator that scrambles. U was just a C0 gate, right? So
this isn't perfect teleportation yet. And actually, the more scrambling U is, so as U becomes more and more scrambling, the fidelity of teleporting actually increases, and the probability of getting an EPR pair decreases, which that shouldn't be too surprising that the probability decreases if our original EPR pair gets scrambled by this operation. What perhaps is a little bit more surprising and not totally obvious is that this fidelity goes up. But roughly the picture, the way I sort of think of this is by virtue of kind of projecting onto this EPR pair here, we've essentially set up a scenario where sort of if you say, conditioned on the fact that I measured the EPR pair here, something very special must have gone in here in order for me to, put Alice's state in here and get back to the original state I had put in here. I need a very special input state here. So somehow I'm building up correlation between this state of qubits Q3 and Q4 and Alice's qubit. And in particular, in the case where this is totally scrambling, then Q4 actually essentially has to be in the state that Alice put in. That's kind of an intuition that's not a full proof. But we already sort of saw this example where if we generate some entanglement here, then the probability that we teleport goes up. And so the bottom line is sort of a signature of scrambling. Okay, the fact that this probability of projecting onto an EPR pair goes down is maybe not that useful because there are other reasons that might go down if you have any source of decoherence. But the fact that this fidelity goes up, that's actually a pretty strong signature that something special happened, right? That you really got the right state out here. And so that can be a useful way of very clearly experimentally having a signature that this operation scrambled, and it's not just that some coherence happened that made a correlation function go down. Okay, because I ran out of time, I will show some data from an experiment with trapped ions at the beginning of next class. I also will say a little bit about how this idea of having two copies of the same state can be useful for measuring entanglement. And then I promised I would, I promised I would give a bit of a survey also of a totally different approach to sort of quantum gravity in the lab, which is what are people doing in the area of precision measurements. So that's a lot, but I'll try to kind of give, a flavor of each of those things next time. So.
Thanks, Monika. Are there some quick questions?
Could I ask a question?
Yeah.
Maybe you could explain one more time. I guess I just didn't quite get this. So what was, why is it the one, this unitary becomes a scrambler that I'm so much more likely to have this bit transported? I didn't quite get that.
Yeah, so when this is scrambling, the key thing is that if this is scrambling, measuring these sort of middle qubits to be in the original EPR state heralds the successful teleportation of this qubit to here. And I guess one way that I think you can kind of start to see it in this example that we did with the C0 gate, where basically like the only way that this pair ends up still in the same EPR state is that if Alice's qubit was such as to flip a bit, this qubit 3 also had to be in a state that caused this bit to flip. So you either needed kind of 2-bit flips or no-bit flips, right?
Right.
And so in that sense, we actually generated by projecting onto this this EPR state, generated some correlation between Alice's initial state and this output port.
Right.
What we didn't yet do is do it perfectly, and that has to do with the fact that the C0, it kind of works in one basis, right? So in that Z basis, you have now this perfect correlation that if Alice caused a bit to be flipped, then we must have been in a state down here that would also cause a bit to be flipped.
but in order for this to happen in kind of a fully, basis independent way, that's not good enough. And but sort of what will work is having a random unitary. And so that's basically the idea.
So as a follow-up to that, so you said, okay, so so now U becomes a scrambler, and we're
Yeah.
going to play the same story, that the probability of this, of bits 1 and 2 being an EPR pair goes down. So then
Right.
it seems like the likelihood of you, because if I understood right, the way that you're ensured that bit 4 is Alice's bit is if 1 and 2 are in the EPR pair.
Yeah.
So it seems like the likelihood of you actually getting the information out goes way down.
So that goes down. And there are actually tricks. And actually, if you look at where did I have the reference? If you look at this paper, they actually have a trick where rather than just doing this projective measurement, they kind of do a search using Grover's algorithm to actually kind of make this thing that would ordinarily be probabilistic become deterministic.
Okay.
So there are ways around it, but sort of maybe the simplest way to think about it is in this probabilistic context.
I see. I understand why that was brought up now. Thank you. Okay.
Yeah. Great. Other questions? Okay, so if not, see you next time.
Thanks a lot, Monica.
Thank you.
Can I ask you a question though before you go?
Yeah.
Yeah. So why is this not quantum mechanics with post selection?